Okay, hello everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Events, a nonprofit agency focused on events for AI safety R&D. The purpose of the monthly series is to facilitate progress in the Guaranteed Safe AI direction. The session is 1 hour, usually half presentation, half discussion. Today's speaker is Louis Jaburi, independent researcher, quite involved in mechanistic interpretability, has been involved in the works compact proofs of model performance via mechanistic interpretability, unifying and verifying mechanistic interpretations, a case study with group operations, and today we'll talk about that and how that relates to guaranteed safe AI. In terms of questions, Louis mentioned it. We can ask questions during the presentation, and there will be time for discussion after. So thanks so much, Louis, for being here. The floor is yours.
Yeah, no, thank you. Yeah, thanks for having me. And let's get started. Yeah, so today I'll talk about some stuff I and many others have been working on that I think is also related or connected to the guaranteed safe AI work. And I hope in this meeting we'll be able to make some connections here. Yeah, I should say that I'm not that familiar with the guaranteed safe AI stuff. I looked into it this week and I tried to understand it, but yeah, so if you have any questions about that, or if you think I misunderstood something, please just yeah, tell me. And let's get started. So the stuff I'm going to talk about will be based on this paper, Compact Proofs of Metal Performance by Mechanistic Interpretability, that came out earlier this year, and which serves as some sort of proof of concept for this whole approach that we're going to talk about today. And some follow-up work based on this paper was one was also by me, and another one again on some toy model. In fact, all of these papers and all of the work that we have done so far is only on toy models, and it's interesting and obviously working towards scaling it up to bigger models and for example LMs. And there are some obstructions towards that we're going to talk about. But at least for these toy models, we have seen some promising results. Okay, so the structure of the talk will be me, first of all, starting with the Guaranteed Safe AI framework and trying to, on a high level, related to what we have been doing, and then get into the bit of the technical details and an overview of the stuff we did. And then at the end of the talk, I want to kind of zoom out again and share some lessons, some key takeaways that we had that I think might be also interested for you. Okay, so this guaranteed safe AI framework assumes that we have some sort of AI and some scaffolding around it, and this is the system we want to prove things about, or we want to generate proofs. And the things we have been doing could be seen as some sort of very closely related or special case of that. And what we did is based, or our question is basically based on removing all the scaffolding and just asking, can we prove something just about a neural network itself? So if you are familiar with the guaranteed CFI paper, the reward model that we assume is just implicit in the training of the neural network, and this is what they call level 0, whereas the verifier is very strict because you want to have very sound and concise bounds on the accuracy, loss, or some other metric that you might care about. And then, yeah, this is level 10. I think we could say that having scaffolding, we were basically very limited or reduced to like this narrow case of like just a single neural network. And obviously having scaffolding around changes your setup, and in some sense it makes your life easier because if you have all the scaffolding that might be helpful in limiting the outputs of a neural network or blocking some stuff. On the other hand, the setup we assume is pretty simple because it's simply focused on the neural network. Okay, but given that we just want to prove things about neural networks, yeah, the question is like, how do we generate these proofs, right? How do we come up with proofs? And now, yeah, with this in mind, with this kind of question in mind, I want to start getting a bit into our work. So just to like fix some notation, some setup, let's say we have a model like a transformer that is trained on a task. And you could think about a language model, for example, that is trained on the task of next token prediction. So X is some sort of set of sequences of some fixed length, and then Y is the most likely next, or the correct next token. And so we are interested in generating formal proofs, which prove statements like this. So we have the accuracy of the model on X, and we want to prove some lower bounds. And here theta is like the weights, right? So each neural network will have some weights, and the bound and the accuracy will depend on the weights of that model. So for example, I have a model that gets like 80% of the inputs correctly, and I want to have bound that this is indeed the lower bounded that is lower bound of that. And so you might think there are two possible there's two proofs that we can always generate. And I should say there can be several different proofs for such a theorem. But two that you can always do. So if you set your bound to be 0, then you trivially get a proof, right? So you're saying that a model will have at least 0% accuracy. And that's not a very interesting statement, although it is very easy to prove. Another proof that you could run is what we call the brute force proof, where you actually prove that the model has accuracy A of theta. So in this case, the proof is that the bound is strict. But this proof works by running all the inputs, right? So you take all the possible inputs in X, and then you send them through your model, and then you see what the model gets, and then you save a trace of that. And this allows you to get the correct accuracy. Uh,
Yeah, we have a quick question in
yeah.
the chat. What kind of object is X? Is this
Yeah.
some kind of nice distribution that we're sampling IID from?
Yeah, for now you can assume that. Yeah, as I said, like you could think of X as just like some space of tokens of a fixed context length. I mean, that might also vary and doesn't need to be IID, but obviously then your proofs will differ and you might need to deploy different strategies. But yeah, like I think one valid thing is just the language model setup. And I will talk about another example in a bit. Um, yeah. And I should also say you might be also interested in bounding other stuff than other things than accuracy. You could be interested in bounding the loss or some other metric that is measurable, and you might be interested in bounding that. But this depends on what you're interested in, and obviously this will modify what kind of proof you have to come up with. And I've chosen to stick with accuracy for this talk, but yeah, you can also do loss and other things. So if you think about these two proofs that we can generate, the trivial proof and the brute force proof, the brute force proof in this sense is optimal because it's as faithful as possible. But obviously we're not interested in the brute force proof. That's something that in real life is not feasible. If we again take the example of like language models, if you have 50,000 tokens and a context length of 20, then you will get like exponentially many possibilities that you would need to check, and that's just not feasible. You don't want to enumerate every possible scenario that you could be in and run that. You just cannot do that. So what I'm trying to say is that something is missing. Like just looking for how accurate, how tight our bound is that we prove is not capturing everything we care about. And what I'm advocating here is that there are actually two metrics that we care about when generating these proofs. And so the first one is obviously how good is our bound? How close is it to the true performance? But the other one is how compact is it? So by compact here, I mean how many flops do we need to verify the proof? And I guess in this sense, when I say proof, you should think about a formal proof that's written in, say, Lean or Coq and can be like formally verified. And these proofs will have a fixed number of flops that they need to run the proof. So for the example, if you do the brute force proof, then you need to check how many flops it takes to run one input, and that includes like all the matrix multiplications and applying all the functions, and then you have to run X many of these inputs, and that gives you the amount of flops. And then typically, yeah, will be something very high. And now having two metrics that you care about, you should think about this as a trade-off. You want to have proofs, you want to generate proofs which lie in this upper left corner. And there's some sort of Pareto frontier that you want to push. Right? So what you can always do is like you can always be on this line here, but you want to be you want to push it to be in this corner. And obviously if your proof is shorter, then you will be forced to have looser bounds. But the hope is that then you can still get reasonably close bounds. So yeah, we care about proofs that are both compact and faithful and accurate. So what is the problem with a brute force proof and like why is it so long? It's so long because we think about this neural network as a black box. We don't make any assumptions about its interior life, and we just see it as some sort of input-output machine. And if you think about the model as just an input-output machine, then obviously you cannot generate many interesting proofs. You're kind of forced to just do brute force proofs. So if we want to have any hope to generate compact proofs, we need better understanding of neural networks. And better understanding of neural networks, well, that's exactly what mechanistic interpretability tries to do. So our hope here is that we can use techniques from mechanistic interpretability to get a better understanding of this model, and then out of this understanding, generating a more compact proof so that we end up in this upper left corner. And I will talk briefly, I'll give a more high-level overview of that. And if you want to have more details or get more into technical discussion, then I'm happy to do that after I finish the talk. Yeah, so as I said, the brute force proof just sees the model as some sort of input-output machine. But our general strategy will basically have 2 points. First, we want to reverse engineer the computations that the model does or approximate. And then we want to bound how bad these approximations can get. So without going into the details of the picture, you don't need to understand it. That if you don't understand it, that's fine. But what you should look at is you want to decompose your model into several components, kind of in a modular way. And you want to find out, or maybe you have an idea what each of the component does. So you're like, okay, this component is responsible that when it gets these two kind of tokens, it performs some sort of computations on them. And this other modular part is responsible for this thing. And what you want to do is you want to, yeah, get some sort of algorithm, reverse engineer algorithm that you believe the model is doing. And if you have that, then this will allow you to generate a more accurate proof, a more compact proof. The main obstruction that I'm talking about here, about the noise, is neural networks are like real world objects and like I mean they're trained on real world data and so they are just naturally messy and they will never exactly implement the thing that you believe them to implement. There will always be even if your interpretation is really good, naturally there will always be some difference between the clean implementation of the algorithm that you believe the model is doing and the actual computations it makes. And so this difference I call noise. And so let's say in this example, yeah, you identified what each of these components are doing, more or less, but each of them will have some of this noise. Then you basically need to make sure that even if this noise adds up in the kind of worst possible way, you still get the correct outcome. And because we're doing, yeah, because we want to have like guaranteed bounds, we need to do these worst case pessimizations. I should say that intuitively, I don't believe that the noise adds up, sorry, that the noise adds up in the worst possible way. But yeah, if you want to have guarantees, this is just something that you have to assume.
Quick question again in the chat. I think you can see
Can you
it.
see what the noise is? Yeah. So you have the weights of your model that you train, and yeah, through some mechanistic interpretability technique or whatever, you find that the model is approximating an algorithm. But the clean implementation of the algorithm and the model's weights is usually not exactly the same as the actual true weights of the model. If you, yeah, you can think about if you have certain examples in mind from coming from mechanistic interpretability, then you typically see that. Even for simple things as models learning modular addition, they do some fancy thing with Fourier embeddings, but usually they don't implement this in exactly clean way. But there's just this difference of like the idealized version of the model and what it actually converges to during training. I hope this addresses the question. Mm, okay, cool. So yeah, let's just recap. First, reverse engineer the computation, and then bound the worst case behavior of the noise. And the basic insight is, if we know what if we can if we know what algorithm it's doing, and if we can prove that up to some like pessimizations, then we don't need to run every input, but we can already infer from that from just the way it's basically that it's doing the correct thing. And I want to share some empirical results on that end. So one example was the Max04 example in the original compact proofs paper, where they took a transformer, and in this case it was trained on the following task. You have 4 tokens, and each token represents a number between 0 and 63, and you need to predict which of the tokens is the biggest one, the max of this sequence. So this is something that the models can reasonably learn, and we can see here different proofs based on the compactness and how faithful they are. And so obviously you have the brute force proof, you have the vacuous proof which will set at 0, 0. And you see something that I've been mentioning before here, like some sort of Pareto frontier. The less flops you have available, the looser your bound becomes. Although it is pretty impressive that you can get from brute force to cubic by reducing a lot of computations, but you still get actually very good bound. And in fact, this scale is exponential. So the Pareto frontier in this case would look like an exponential curve here. So we really pushed the frontier here. But yeah, you obviously see if you pessimize too much, then at some point you get almost vacuous or very bad bounds. Mm. Another example from my paper is, yeah, you get kind of a similar picture. You train models on some group operation task. So this is related to the crocking setup if people are familiar with it. If not, that's fine. But you see a similar picture. You have the brute force proof, which retrieves the exact accuracy, but it takes longer to run. But we are able to reverse engineer the algorithm that the model learns, and then we get sometimes actually very good, exactly the same bound, exactly the same, yeah, accuracy that the model gets. And sometimes we're just off. So that's another thing. Sometimes your interpretation is off, the noise is too much, or like your pessimizations are too strong, and then you will just get vacuous bounds. So what are like the problems with this, right? And why can't we just now throw this whole stuff on like GPT-2? What's stopping us? Well, first of all, one like difficult thing is, or like the like one of the main abstractions is again, yeah, like like assuming that the noise behaves in the worst ways really makes your life much more difficult. So in this picture, you see four matrices, and each of them will have some noise. So which might be not very big, but if you assume that they add up in the worst possible way, then numbers can become big very quickly. So you see this here. You make some pessimizations over like some internal matrix multiplications, and if you're allowed to use quadratic complexity, so if you allow yourself enough flops to do that, then you get decent results. But as soon as you go like into linear pessimization, or well, sorry, when you are only allowed to use linear many flops, um, then things become very badly, and like it explodes. Like 97 is a super bad bound compared to the rather lower ones. It's like, yeah, 1 to 2 order of magnitudes bigger. And also, as models become bigger, they will have more components, more branches, and you have to also just worry about how generally these different branches will interfere with each other. And more layers, deeper layers will imply that this will become a bigger problem. And before I talk about some ideas on how to approach them, I want to say what our vision is, or where we think this compact proof approach is useful. So our goal here is really to evaluate and quantify interpretations. So we have this big problem in mechanistic interpretability that we reverse engineer these kind of algorithms, or what we believe the model is doing, but it's very hard to actually say if that's true or not, right? So if your model is almost doing what you think it does, but there's a discrepancy of like somewhere there's a discrepancy of like 2 or whatever, maybe this is important. Maybe the thing that you don't understand that you believe is unimportant actually matters. And it's very hard by just looking at this and just by like qualitatively looking at stuff to measure this, right? You have this problem also just for sparse autoencoders, where we just don't know how much actually they're useful or helpful. And being able to quantify them is actually even nicer, where we want to, yeah, know that we always want to quantify both the faithfulness and the compactness. Because if you only optimize for the one or the other, yeah, then we get the brute force proof or the vacuous proof, and that's not very useful. And like where we want to end up with, like once we address these problems that I mentioned on the last slide, we want to be able to automate this whole process, right? So once we can quantify interpretations, we can automate them. And on the other hand, if we ever want to automate interpretations, we need to be able to measure them. We need to be able to quantify them. And I believe in the future, as models will grow bigger, interpreting models will become more messy and more difficult. And like one way to try to escape this is to just, yeah, automate this whole process. Right. And let me say something about the fine-tuning that I mentioned here. So one way to try to avoid this noise problem is to take your model, right, and you train it, so you end up with this trained model. And now instead of further training the model on its original loss function, you want to train it to become, you want to train it on the bound. So if I go back quickly to the slide here, so this bound is just a number that is dependent on the weights, and it's a real number. And in fact, in the proofs that we have at least seen so far, this process, this association of a weight to its bounds is a differentiable process. So instead of trying to train on the loss, you can try to train on this bound. So you can try to train the model to get a better bound instead of just training it to get a better performance. And what we hope to get out of this is that the model becomes more interpretable without having to pay in performance. And we're trying to make the model fit our interpretation once we have an interpretation. Okay, so that's a lot of technical talk. I want to kind of zoom out again and yeah, just share kind of 3 takeaways that I hope you kind of remember from this talk. And yeah, happy to discuss these obviously. So one is, yeah, generating proofs can be easy. Maybe that's a bit of a provocative statement, but like, yeah, you can always write down the brute force proof. But what's really interesting is like generating compact proofs. And so like the length of the proof itself is an interesting and an important metric. Second point is, yeah, understanding and compression are closely linked. So this is true for neural networks because and compact proofs. So neural networks can generalize from their training data. And so they see some pattern there and they're able to learn some sort of algorithm that is able to compress these patterns. Right? So big models don't just do memorization. If they would just memorize, we could probably not do better than the brute force proof. But because they find patterns and exploit these patterns, they're able to generalize. And so likewise, what compact proofs try to do is recognize these patterns, recognize how these patterns manifest in the model, and use these to generate the more compact proofs. And it's always the ideal relation is better understanding, more compact proofs, and more compact proofs mean you have a better understanding, at least on this predictive frontier. And the third point is, yeah, if it's too difficult to generate good proofs, or if your proofs lead not very useful bounds, then you can try to change the system to match your proof. So in this example I was just mentioning, you can fine-tune the model on the proof bound to become closer to your interpretation. And more generally, yeah, you have some agency or like some ability to adjust the model in hopes of getting better proofs. Okay, that's kind of the three points. I want to briefly mention also, if you're interested in this and to learn more about it, you can obviously go and look at the papers. I also made a tutorial that is linked on my website. You can also just Google my name and find me there. And yeah, on the notes tab, I linked to a tutorial that is meant as some sort of gentle introduction to how would you even do such a thing in a very simple setup where you can write down the math and like try to understand it. And I think I'll stop now and yeah, open it up to the crowd. Yeah, if you have questions, if you want to discuss something, yeah, happy to.
Yeah, so thanks so much for the presentation. In terms of time, we have about half an hour, so I guess plenty of time for discussion. There is a question actually.
Okay. Yeah, no, I'm happy to go into details about the fine-tuning the model on the proof bound. So I'll also admit that that's a really crazy thing to do. And it took me also like some time to actually appreciate that. So you like when you generate these like a proof of such a statement can be thought of as a function from the space of weights into the real numbers, which takes a weight and computes this bound. And so your proof will tell you how to compute this bound. And it will look something like this, like take the weights of this matrix and take the weights of that matrix and then multiply them in a weird way or do like some weird manipulations. But like at the end of the day, you will end up with a number. And so, for example, in the brute force proof, this number is computed just by by just taking the sum of f of x and then checking the accuracy, or if you're interested in the loss, then checking the loss on that on this, on all the inputs and sum that up. So in this case, b of theta would be just your original loss function. But as I said, more compact proofs would do something, yeah, usually do something more sophisticated or yeah, less obvious. And so in that case, computing this bound from the model weights will be a different process. But this process happens to be differentiable as well. And so we can do backprop on differentiable functions. And so I want you to think of this as your new loss function. So this is typically better thought of when you try to bound accuracy instead of accuracy. When you try to bound loss instead of accuracy. So for the fine tuning, yeah, this should actually read loss and not accuracy. But yeah, so in that case, you replace your loss function by this bound. And so what happens when you fine tune on this bound? What happens when you train on this bound? Your bound becomes better, and there are two ways to achieve this. Either your bound will become more faithful, so that your bound will come closer to the true accuracy of them or the true loss of the model, or your model will perform worse to become more close at your bound, which is worse. But what we have seen empirically, at least so far, is that in fact the model will just will actually match that the bound will start going up and actually match the true number, and it will not decrease in performance. And because your bound incorporates some sort of interpretation, some sort of assumptions that you make about the model, something like this part of the network is responsible for this thing, a tighter bound means that your assumptions on the model are more accurate, are more faithful, are more true. And yeah, that's a good thing, obviously. How does the fine-tuning process change about? Yeah. So, I mean, obviously, like in some sense, when you fine-tune on the bound, just naturally the weights of the model will change, right? So after each time you train on this bound, just as it is like some sort of new loss function, you do backprop and then the weights will change. And so you end up with a new model. And then you can compute the bound of that model. And that's going to be a new bound. Similar to just how you train on a loss function. You do like one run, you do backprop, you have now updated weights, and then you iteratively repeat that process. Yeah. Okay. I see there's some more questions.
Maybe actually, for the sake of the recording, I'll just read the next question if you don't mind.
Yeah, please.
Yeah. So, can you use universal function approximation or related theorems to prove model performance if you have some idea that what true function each component in the model is approximating?
Yeah, thanks. So universal function approximation is not helpful because it's not telling me something about a very concrete function. So what does universal function approximation theorems say, if I have like the space of polynomials or like some other space of functions, then I can always approximate a very specific function. And that in some sense that statement is too general because we want to know if I have a very concrete set of weights, what approximately is this function? What is approximately is this model with these weights doing? This is a more specific requirement or more specific question than about thinking about the whole space. I mean, if you think about it, neural networks are obviously universal approximators. So they should be able to approximate any, I mean, with reasonable amount of weights, they should be able to approximate any task. But this is not helpful for us in generating proofs because yeah, we always have to worry about concrete weights.
Okay. Can you elaborate a bit on the assumptions you are making about your model and what the cubic subcubic proof is on slide 10?
Yeah. Yeah, thanks. So I'll try to, yeah, so what we do basically is we make use of the transformer architecture. So a model is like a one-layer transformer, and we'll have like an attention part, like an attention QK part and OV part. And so this part, for example, will tell us how much attention is paid to which token. And for example, this part here will be very structured. If you look at this matrix here, you will see that bigger tokens will always get much more attention. And this part here will be responsible to say, hey, take the token that is paid most attention to and just use that for your output. And this is basically the kind of decomposition. So once you know that, once you know that and you kind of find reasonable ways to prove that actually this is what's happening, this is in some sense enough to validate it. Because yeah, now you don't have to worry about every input anymore. Once you know that what it's doing is just this part is looking at what token is the biggest, and this part is looking at, or what this part is doing is take the token that QK tells me is the biggest and just output that. So this is like an example of like how an algorithm or an reverse engineered algorithm can tell you or can save you some compute because now you don't have to run inputs anymore. Like if I were to hard code this, yeah, that would very clearly give me a very valid way to solve this task. And yeah, so what we're assuming basically that the attention is always paid to the biggest token, and that this part is responsible for copying the biggest attention, the token that has the biggest attention to it. Yeah, I also don't know what y'all background is, so if you want to have more or less technical details, also let me know. Obviously, I found the trap where I get too technical too quickly.
Actually, there's Devin asked for more
Yeah.
questions, which I'll just read all in a row. Um, what are some examples of useful compact proofs of model performance? Why use mechanistic interpretability to gain leverage for proofs and not some other mode of understanding neural networks? For example, something that looks more like deep learning theory. How much do the proofs in the max of 4 or the group operations examples depend on the particular task? How does this line of work interact with sparse autoencoders?
Yeah, thanks. All of these interesting questions. I'll just go through them one by one. Yeah, so what are some examples of useful compact proofs of model performance? There are none. That's a quick answer. As I said, the work we have been doing is on toy models and scaling this up is something we're intensely working on, but we're not there yet. Yeah, we started basically with these kind of proof of concepts, and now we're thinking about how to actually get useful things out of that. And maybe this also answers your second question about why use mechanistic interpretability to gain leverage for proofs. So well, first of all, for the application we are interested in, which is to evaluate and quantify interpretations, and specifically bottom-up interpretations, obviously these will come from mechanistic interpretability. So, when I talk about compact proofs of model performance via mechanistic interpretability, you could be interested in like getting formal bounds on the models, but you could also be interested in evaluating and quantifying part. And so for that second part, you want to look, this is specifically tailored towards mechanistic interpretations. But of course, you could, one thing you think about is also using, instead of what's related to deep learning theory is, instead of using proofs, you can try to use sampling and like smart sampling informed from your understanding of the model, maybe some pack bounds, this kind of stuff. I think that's something that at least Jason thought about, but I don't thought too much about. But yeah, like there's probably some things you can try. But I should warn you, like big abstraction theorems like universal approximation theorems will not be helpful, because at the end of the day, for each possible set of weights, you need to generate a sound bound, and it should be like a good bound, reasonably, or like a tight bound. And so this implies naturally you would be biased towards using understanding of models which talk about weight specifically. And so mechanistic interpretability does exactly this bottom-up approach. Okay. How much of the proofs in the max of 4 or group operation examples depend on particular task? Yeah. So the group operation example does depend on the specific task. So in this case, it's like multiplying learning group operations on S5, but you could also try to do this for other kind of groups, and then that would work. But you are constrained to this problem. The max of 4 can be generalized. Well, I don't think this is something we have, or I've thought too long about, but I think this should generalize to any, let me go to this slide. This can probably be generalized to any task where you have a set of tokens, and then the correct token that you output is already in your input. Right, so for example, the max of the tokens the max of the tokens that you receive will always be in the input sequence. And I think for any other tasks, such as, for example, the min of the tokens, that most of the stuff should go like almost verbatim. Things that would probably not, something like the average, or maybe not the average, but like GCD or some other task like that would probably not work exactly, or like it would be more difficult to generalize in that situation, because the greatest common denominator of a sequence of numbers might not be in the sequence itself. Okay, how does line of work interact with SAEs? Yeah, I think this is an interesting question that I think we're trying to address, and that basically is about this trade-off. So SAEs also have a period of frontier where you have sparsity and the loss reconstruction, and you want to also be in an optimal case where obviously the more sparse you are, the worse your loss reconstruction is, and you want to find the optimal point on that frontier. And we don't know what the optimal point is or how to classify that, right? If I say USE has a reconstruction loss of like 0.3, but sparsity 1 and like L1 sparsity 1, but I have a second one which has like reconstruction loss 0.5, but sparsity 0.8, that or sparsity 2, then you don't know what to do with this information, right? Obviously, if I tell you like it has reconstruction loss 100, but like very low sparsity, you will still say that that kind of sucks. I don't want to do that. But formalizing this and yeah, finding a way to be able to measure this is something that we can try to do. So take your SAE that you trained, and then this is still high level. Like I don't know, I don't know the details, but take your SAE, train it, see what interpretations it gives you, and see if you can turn interpretations into proofs and see where they lie on this kind of graph. And hopefully you see some sort of pattern, or you also see some sort of Pareto frontier that is represented in there. Thanks for the questions, by the way. Yeah.
I have one or two questions. I'm wondering if you've given thought of essentially using the extracted interpretations, instead of reaching for performance bounds, trying to go towards more safety properties.
Yeah. At least I haven't thought so much about that. I think the first thing you need to figure out is how do I formalize these safety specifications? And then the important thing is it should be something that's measurable. Like the nice thing about bounding accuracy or loss is just something like you can mathematically operate on. I think the case of like being more explicit about the safety specification is definitely like interesting and something that I think will become more important, but I feel at this point we're not far enough yet to be like to prove such things. I think in some sense it's at least for these time models and in the beginning it's easier to just try to bound the accuracy and the loss. And I mean there might be situations where this would be sufficient for your safety specification, right? I mean I like if you just want to have correct output, but provably correct output 80% of the time, then this could immediately be applied to. If you have a more complicated safety specification, that will look different. And then you need to think about that. But then I would assume also you have more scaffolding. And then I think you would need to restructure this whole thing anyway a little bit. I see some more questions. What makes you want to work on this line of work? What gives you hope that it will ultimately become useful for frontier models? Yeah, thanks. So here's my line of thinking. Mechanistic interpretability is a potentially very powerful tool, and I think we're heavily invested in that. But there's some fundamental problems, and one fundamental problem is like the ability to measure interpretations and to evaluate them in a rigorous way. And in general, we see problems where people use mechanistic interpretability to reverse engineer circuits, and they're like, oh, this part is responsible for this kind of language task. And then like a few months later, you see like a follow-up which says, oh, actually, that's not what's happening. Like, sure, you did a lot of work and like you found a very nice computational graph that kind of does what you claim it to do, but this is not the full story. And these kind of problems are addressed by compact proofs. Now, I'm not gonna say like I'm confident that compact proofs will be like the solution to that, but I think if you like the problems it gets at, and the problems you might see when you try to scale up compact proofs, I think are problems that are more could be of more general kind. Like sure, some of them might be bound to the specific details or the specific setup that you work in using this compact proof approach. But some of the problems of like how do I rigorously scale up a bottom up reverse engineering process? I think this is a general question that is exciting to work and important to work on. And this I think is one of my motivations to do that. Why focus on worst case instead of expected case plus some error margin? I mean, yeah, okay, sure, but what's the error margin? Do you like I think yeah. I agree that also most likely a version that is scaled up will be more of the form, will be more like will be less strict. And people have worked on that. I think the Alignment Research Center is doing stuff on that. I mean, yeah, if you think about it, there's like some sort of spectrum where if like worst case and average case, and mechanistic interpretability is at the average case, and like this compact proof approach is on the worst case, and both things have like their issues, and ideally we hope to find something kind of in the middle. And yeah, as I said, this could be like we're using like some sort of some sort of sampling, or yes, some other kind of similar technique. I think we did worst case because, I mean, first of all, we want to see how far we can take it, just see what the limitations of that are. And yeah, I mean, also to establish some sort of baseline, like how difficult is it actually to get these kind of guarantees? And for that, yeah, you have to assume worst case. Okay, one more question. What do you think is the most likely way that this line of work does not succeed in its goals? Yeah, I mean, on a high level, obviously just scaling it up. And I think more precisely, so I don't know about like most likely. I guess there are like several things. I don't know how I put the probabilities on them. So one thing that could happen is that just the fine tuning doesn't work, right? So maybe you fine tune your bound, and then the model kind of does adjust more to the interpretation, but the model then becomes worse at its performance, and you have like the interpretability tax becomes too high. I think this could be a real problem, and I think yeah, we have some ways to. I think we have some ideas to avoid this exponential branching, but they might also just empirically fail, and then we're also done. Yeah, I think. I guess generally all of it, and I've been saying this repeatedly, like all of this comes down to like some sort of issue with the noise. And yeah, and maybe also to make a reference, I think this issue with the noise is not specific to compact proofs, but generally to the process of doing mechanistic interpretability. Like the question of how you deal with noise, I think is always persistent, and you have to find some way to deal with it.
I'm also just wondering because well, I appreciate the presentation but I also wonder if as you came to understand the guaranteed safe AI direction, if you just have like general ideas of the interplay between the two research directions that could be interesting to mention.
Yeah, I think if we're able to scale this up, to say LLM-sized models, this can be pretty powerful, right? Like this will make your life here. This will make your life here easier if you have a lot of control over this part. And I think usually the scaffolding all around this is happening exactly because it's hard to just control an AI by itself. Like to just understand and get reasonable bounds and guarantees of a neural network itself. That's just typically something more difficult. So the better we are at this process here, I think the easier our life becomes for like the other stuff. If I can tell you that your LLM will never output a token X, then maybe this will relax the safety specification. This will make your deployment infrastructure easier. And kind of, yeah, just obviously will not get rid of all the kind of proofs that you would still want to do, but would simplify your life. And I think, yeah, I think this auto-interp agenda is also closely related to the guaranteed safe AI stuff. At least I've seen it also mentioned and discussed in the paper. So if that's something you care about, automating interpretability. I mean, yeah, if you have such a thing, most of the stuff will be automatic, right? Like you don't want humans. Like, well, when the AI is deployed and then like in specific in high stake situation where things happen very quickly and many things happen very quickly, you cannot afford a human to be involved in this kind of process. So you want to automate make things automatic, and in that case, you are forced to quantify things. And so one thing you might be interested in quantifying is like, is there some part in the model in the neural network that is responsible for harm? And in that direction, you could be thinking about you would go towards the automating Mech-Interp agenda, and so that's something where we are working towards too. I see one more question. What was the story by which you came to work on this topic with Jason and others? Yeah. So I guess I can only confidently talk about myself. I I started, I mean, I have a background in pure math. I did a PhD in pure math, and I started doing AI safety, interpretability work over the course of like 1.5 years. And this seemed like, I mean, obviously it seemed interesting to me. It also seemed like something where I can, and then addresses like a fundamental question, and that's something that I'm like attracted to as a mathematician in any case. And yeah, like I think that's also something where I probably have some competitive edge and where I can bring in some experience. I think, yeah, I don't know the details, but I think, I mean, Jason actually has a background in like formal verification. And he has worked a lot with Coq. And so I think his thinking maybe was like, yeah, if I can apply formal verification to X, then why can I not also apply it to like this setup? But you would have to ask him for more details.
Cool. Well, I think we're about time. So thanks so much for the presentation, Louis, and thanks everyone for participating.
Yeah, thank you.
Yeah, have a nice end of 2024 as well. Farewell.
See ya.